So in the last video, we talked about the fact that we can undergo reactions with aromatic compounds. With electrophiles, they have a tendency to undergo substitution rather than addition. And in these reactions, even though aromatic compounds like benzene are not very good nucleophiles, we have little tricks where we can soup up our electrophiles. We need strong electrophiles in order for benzene or the aromatic compound to act as the nucleophile. And the first step in the reaction just involves the nucleophilic attack from the electrons in the aromatic system with the electrophile. So as we saw last time, we get that nucleophilic attack to form this intermediate. We can call that the sigma complex, or we can call it an Arenium cation. That's followed by something comes along and removes the proton, and the electrons in the carbon-proton bond reorganize to reform the carbon-carbon double bond, and upon forming that carbon-carbon double bond, we get what we call re-aromatization. So we talk about this as being an electrophile, electrophilic aromatic substitution reaction. And the result is just the substitution of a proton by the electrophile. In step one, the electrophile is attacked by the aromatic compound to form the sigma complex to one of the carbons in the benzene ring. Here we're seeing, as I said, most of the time it's not a naked positively charged electrophile. Most often it's some sort of complex, some sort of Lewis acid base adduct, and the electrophilic portion reacts with the nucleophilic aromatic compound. We get this Arenium ion intermediate, and even though we're breaking up the aromaticity, we're forming something higher in energy, it's still relatively low, and we still have a high degree of delocalization. We can draw these different resonance structures and see that we can distribute the charge amongst 3 different carbon atoms, so we have quite a bit of charge delocalization. So this is a stable complex, the sigma complex. It's not as stable as the starting material, it's higher in energy, and we release the nucleophilic part of the Lewis acid base adduct. Again, we have this high degree of charge delocalization. It's pretty evenly distributed amongst these 3 positions, most of the charge, and that's where we're going to see the reactivity of these Arenium cation intermediates. The next step in the reaction just involves our base now acting as a Bronsted base and pulling off the proton of the sp3 hybridized carbon. And when it pulls that proton off, the electrons in the carbon-proton bond reorganize to reform our carbon-carbon double bond, and when that carbon-carbon double bond is reformed, we get re-aromatization, and the reaction often is favored thermodynamically. We get a little bit of energy released in the reaction. Here we see the energy profile again. So let's just take a closer look at this energy profile. So from here to here is the first step in the reaction. Our aromatic compound acts as a nucleophile. There's quite a barrier to this reaction. This is just showing what the transition state may look like. As the electrophile approaches, the electrons begin to migrate, and we get rehybridization of this carbon from sp2 to sp3 in the intermediate Arenium cation. That Arenium cation then can act as a Bronsted acid and give up this proton. The activation barrier for proton transfer reactions, as we know, is typically quite small, and in this case the proton gets removed and we've replaced that proton with the electrophile. So they're usually slightly exothermic, although endothermic reactions can also be induced to occur by adding energy in the form of heat. So here we see the overall mechanism. We have our nucleophile reacting with our Lewis acid base adduct at the electrophilic portion. We get an intermediate, which can then act as a Bronsted acid, and we remove that proton. That proton gets removed by the basic portion of the adduct that was kicked off, and we get re-aromatization, but we've now substituted the proton for the electrophile. This is the rate determining step, and this is fast. So this is the general mechanism, and it occurs for lots of different reactions. As we go through, we're going to talk about some of these reactions. We can do halogenation reactions. We can do nitration reactions. We can do a sulfonation. We can add alkyl groups. Now, remember, each one of these has to be made electrophilic. So you can think of whatever this was as a cation. So in this case, the electrophile was either a nitronium cation or some adduct which makes the nitronium very electrophilic. Same with the sulfonate group, the protonated sulfonate group. Here we're just adding an alkyl group, so probably in the form of a carbocation. And in this case, we're adding an acyl group, probably in the form of an acylic cation. So let's take a look at some of these reactions. The first one we're going to take a look at is nitration. So the aromatic compounds are quite stable, so we need very reactive nucleophiles. As we've said, we need reactive electrophiles because our nucleophile is not very reactive. From a mechanistic perspective, this is the part that perplexes students. So you'll see that here, when we think of nitric acid, we think of a proton leaving and the nitrate being the anion. So how do we make the electrophile? This is the part that I think students find the most trouble with, is figuring out how the electrophile is formed. What is the electrophile? So in this case, nitration occurs by using nitric acid is the source of the electrophile, and sulfuric acid is the acid catalyst. Let's take a look at how this might occur. It's kind of interesting because in this reaction, our nitric acid is acting as a base. So here we see the Lewis structure for nitric acid. You guys should probably practice drawing that. But nitric acid, even though it's fairly acidic, it's not as strong an acid as sulfuric acid is. Sulfuric acid is a much stronger acid. And in this instance, we have concentrated sulfuric acid with the addition of some nitric acid, and our nitric acid is acting as the base. Lone pair of electrons on one of the oxygens of the nitric acid, just remove a proton from sulfuric acid, and we get the protonated nitric acid and the conjugate base of sulfuric acid, which we haven't shown here. This thing can then rearrange, and it rearranges by an attack of the electrons on the nitrogen, and at the same time it kicks off the elements of water. When it does that, when it kicks off water, the positive charge stays behind and we get a nitronium ion. Nitronium ions are very strong electrophiles, and this is the electrophile that gets attacked by the benzene ring. So now the mechanism is just the same as it was for the reaction with bromine, in which case we formed an electrophile, a strong electrophile. We do the same thing here. We form a strong electrophile, so a weak nucleophile like benzene can react with that electrophile, and in this case we get formation of a carbon nitrogen bond to form our sigma complex. Again, that charge is delocalized, and then something, in this case water, maybe the conjugate base of the sulfuric acid, something comes along and pulls off the proton from that Arenium ion intermediate. When we pull off this proton, the electrons in the carbon proton bond reorganize to form carbon-carbon double bond, and upon formation of that carbon-carbon double bond, we get re-aromatization occurs, and we've substituted this proton with the nitronium. We can also do a sulfonation reaction. There's a couple of ways we could do this reaction. In this case, again, the nucleophile is the aromatic compound, and the electrophile is either sulfur trioxide or some form of sulfur trioxide. This reaction is quite reversible, as we'll see. If we do the reaction in concentrated H2SO4, we get pretty good yields, but not terrific yields. We get about 56% yields. However, we can get high yields by using fuming sulfuric acid. Fuming sulfuric acid is just concentrated sulfuric acid, which has been saturated with sulfur trioxide gas. We just bubble sulfur trioxide through it, and then we get fuming sulfuric acid. So what's the mechanism? Well, let's talk a little bit about sulfur trioxide first. I'm sorry. So sulfur trioxide is a very good electrophile. It's a good enough electrophile that it could probably react with benzene all on its lonesome. And that's because the sulfur oxygen pi bonds are the result of overlap of the 3p electrons in a 3p orbital on sulfur and a 2p orbital on oxygen, and it's inefficient, so there's a large degree of polarization in that pi bond. And in fact, you'll often see we can draw resonance structures. Remember, sulfur can expand its valency beyond an octet. In this case, we see 12 electrons around the sulfur. But we can draw resonance structures with 5 or 10 electrons around sulfur and 8 electrons around sulfur. And in fact, the sulfur trioxide molecule has a large degree of positive charge on the sulfur atom. Calculations show it to be slightly above 2 plus. And the negative charge is dispersed over all 3 oxygens. So we have a very good electrophile. A popular mechanism has the sulfur trioxide as the electrophile, and we get the addition followed by removal of a proton from the Arenium ion to form this sulfonate, which would then just pull off a proton. It's showing here pulling off a proton from water, but more likely it would pull it off of sulfuric acid to get the benzene sulfonic acid. This is a popular mechanism which you'll find, although I don't think it's the most likely mechanism. More likely, in fuming sulfuric acid, we have a large equilibrium between the sulfur trioxide acting as a base and pulling off a proton from sulfuric acid to form the protonated form of sulfur trioxide, and this would be a very good electrophile indeed. So this electrophile then gets attacked by the aromatic nucleophile to form our Arenium cation, which then just loses its proton and reforms that carbon-carbon double bond. When it does that, it re-aromatizes, and we have our substituted compound, in this case, benzene sulfonic acid. The reaction is most often done in fuming sulfuric acid because we get high yields, and the active electrophile is probably the protonated sulfur trioxide formed in step 1 in this case. We can also do the reaction in concentrated sulfuric acid, and in this case we have a disproportionation reaction. This is much like the autoionization of water to form OH minus and H3O plus. So we have 2 molecules of sulfuric acid. One of them will act as a base, and it will pull off the proton from one of them acting as an acid. We get this disproportionation reaction where we form the protonated form of sulfuric acid and the deprotonated form of sulfuric acid. This thing then can just lose water, and when it loses water, you can see that we get the protonated form of sulfur trioxide, which then becomes our electrophile and gets attacked by the aromatic system to form the Arenium ion, and the reaction from there goes as before. As we mentioned, this reaction is quite reversible, and the direction is controlled by the addition or removal of water. So the fact that water is one of the products here helps us to explain why this reaction goes in somewhat lower yields. The reaction, as we mentioned, is quite reversible, and we can remove this just by diluting using dilute sulfuric acid in an aqueous system. Why might we want to do this? Well, we'll see later on that we often do this to block that group in synthetically to do other electrophilic aromatic substitutions, and we'll see what I mean by that a little bit later. The next reaction we're going to talk about in the next screencast is going to be the Friedel-Crafts alkylation and acylation reactions.